Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Elastic Forces and Other Forces of Nature. Please be an attentive learner as you watch this video. Elastic forces. Okay, earlier we talked about the concept of force, and one of the things that we talked about but didn't discuss any further, but we'll fix that now, is that we mentioned that some forces can be applied to a solid object, and sometimes when they're applied to a solid object, they can deform the object. In particular, we discussed the use of a coil spring in a device called a spring balance that can be used to measure the magnitude of forces. So we're going to talk about springs. So here is a spring attached to a block, and what we have is an equilibrium position which we're taking to be x equals 0, and the spring is neither stretched nor compressed. But now what we're going to do is we're going to take this spring and we're going to pull it this way. Now what happens is the magnitude of the spring force is proportional to the displacement. And again, this can be verified by experiments, but that's what's going to be the case. And so here, when we do that, then the force of the spring is tending to pull you back as you move out to x. And if you went out to x, what would happen is that that would be twice the force of the spring, because associated with the distance, because the more you pull out, the more the force of the spring pulls you back. And so, that happens when you're pulling the swing this way, but the same thing happens when you push the spring in. When you're pushing the spring in from its equilibrium position, here I'm going into the minus x, but the spring is pushing you back out this way. So these are examples of elastic forces. Again, you can pull the spring or push the spring, and you still have forces. The numbers associated with the forces can be found, and the elastic behavior of springs is described by Hooke's law. Hooke was a scientist back in Newton's day. So the magnitude of a spring force, F sub spring, SPR, is approximately proportional to the distance delta L by which the spring is either stretched or compressed. So we say that F of the spring is equal to K times delta L, or the change in L. Now, K has units of Newton per meter. It has to make this be newtons. And delta L has units of meters. Now note, K is a positive constant called the spring constant. It really depends on how stout your spring is. What's the spring made out of, and how many coils per inch, things like that. It is a measure of the stiffness of the spring. The spring always pushes back to the equilibrium position when compressed, and pulls back to the equilibrium position when stretched. We use these two rules to determine the direction of the spring force. So this is the equation you want to know and use. Let's look at an example. In this example, we will consider the forces that come into play in a spring balance. Suppose that a spring balance is used to weigh fish, and it's built with a spring that stretches 1 centimeter when a 12 Newton weight is placed in the pan. Now make sure that you realize, and that's the calibration of the spring, but make sure that you realize the units are important. So I said centimeters. Okay. So then the question is, when the 12 Newton weight is replaced with a 1.5 kilogram fish, what distance does the spring stretch? You know what to do. Let's see how you did. You could draw pictures. So this was the calibration of the spring. So it goes 1 centimeter when that is 12 newtons. But now what we have is we're saying how much does it stretch from the equilibrium. And the equilibrium is just when you have the empty pan, when you put a 1.5 kilogram fish there. And of course, going down with this fish, you have a force that is the force of weight, and that is m, the mass of the fish, which is 1.5 kilograms, times the acceleration due to gravity. Okay, so we're going to, and from a physics diagram point of view, then you have this weight is balanced by, or this force is balanced by that force. Okay, so you're going to use Hooke's law. F of the spring, which you see up here, is K delta L. And you say, well, we do need to know the force constant K. There are ways to do that without knowing that, but certainly finding it is fine. So what we're going to do is the problem states that the force of magnitude 12 are required to stretch the spring 1 centimeter, delta L, and 1 centimeter is 1.00 times 10 to the minus 2 meters. So K is going to be, we plug in the numbers, and you see K, we just take the force of the spring divided by delta L, and we get that this is 1200, but this is newtons per meter. Notice that we changed the centimeters into meters to do this. So the weight of the fish is m times g, so that is 1.5 kilograms. This is 9.80 meters per second squared. That is 14.7 newtons. Okay, so the force up equals the force down. So minus mg, we're taking that to be negative going down, is plus the going up. So we have 14.7, that is m times g, that is minus 14.7, plus, this is the spring constant, 1200 newtons per meter times delta L. So this is a linear equation that you can solve for delta L, and delta L is equal to 0.123 meters, which is the same as 1.23 centimeters. This is a good example of Hooke's law. Let's have you do another problem. You've just bought an inner spring mattress that contains coil springs in a rectangular lay, 20 coils wide and 40 coils long. You estimate that when you lie on the mattress, your weight is supported by about 200 springs, and that's about 1/4 of the total number of springs in the mattress. You observe that the springs compress about 2.6 centimeters when you lie on the mattress. Assuming that your weight is 800 newtons, is supported equally by 200 springs. Find the force constant of each spring. We're assuming the springs are identical. You know what to do. Let's see how you did. Okay, so you need to find the spring constant. So there were 200 springs that were balancing with the 800 newtons, and this is the force of each by Hooke's law. So this is 200, that's how many springs there were. This is K delta L, and then this was the 2.6 centimeters. And then notice that I changed it to meters because I want it to balance with the newtons. So I can solve this for K. So I'm going to divide both sides by 200 times 2.6 times 10 to the minus 2. I do that calculation, I get K is equal to 1.54 newtons per centimeter. Here's another problem to test your understanding. This problem is called Spring on the Moon. An astronaut standing on the moon hangs a 5-kilogram mass from a spring. If the spring constant is 320 newtons per meter, how much does the, that says string, that's supposed to say spring, stretch. The acceleration of gravity on the moon, by the way, is not the same as on the Earth. It's about a 1/6, or in fact, they're telling us here to use the number 1.6 meters per second squared is the acceleration of gravity on the moon. You know what to do. Let's see how you did. So the downward force on the mass is its weight, which is m times g. The upward force on the mass is that of the spring, which is K delta L. Since the mass is in equilibrium, the two forces must be equal to. Therefore, delta L is equal to m times g. Now this is the gravity on the moon divided by k. And so I use the mass, I use the 1.6 meters per second squared, and I use k of this, and I get that this is 2.5 centimeters. We now turn our attention briefly to forces in nature. The historical development of our understanding of forces found in nature has placed them into four distinct categories, and we've talked about two of them. And the other two involve pretty serious particle physics and astrophysics. And so we really don't observe those without equipment to help us make those observations. So we have gravitational attraction that we talked about that keeps things in the universe, and also we talked about the potential energy is going to be mgh from this, and mg is the gravitational interaction. We really didn't talk about electromagnetic interaction because that really doesn't happen a whole lot in ultrasound, although we will mention this just briefly when we talk about the transducer, which has some electrical kind of components happening. But gravitational electromagnetic strength interactions differ enormously in their strength. Gravitation happens at long distances and is relatively weak. These happens at small distances and are relatively strong. On the strong interaction, these are internal to the atom, and these are called nuclear forces. And finally, there is weak interaction, and this force plays no direct role in the behavior of ordinary matter, but is of vital importance when we talk about quantum mechanics. And one of the most ambitious goals of physics, which is pursued by physicists and mathematicians all over the world, and this involves string theory, is to try to have one unifying theory for all of these forces, and this is called the theory of everything as a joke. And there was a movie about that, about Stephen Hawking's, and it was a pretty good movie. And if you ever want to learn more about this, often they will have talks at Fermi Labs in Batavia, where they're talking about these great unanswered questions. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.